Hey everyone, it's Mr. Chung. It's Friday, September 25th, and I am recording the lecture for chapter 1.3 and 1.4. My first time recording online. So yeah, let's see how this goes. So these notes will be for your problem set 1, which I'll upload to Google Classroom and you'll have to worry about. But yeah, I'm not going to do much editing, so hopefully I don't screw up too many times. But yeah, let's get to it and talk about chapter 1.3 to 1.4. So, oops. So let's start with key questions. I know some of you guys had questions about this, and like I said, you guys need to learn how to take notes in your book and learn how to pick up the most important information from your book. Now, the nice thing about the book that you have is that each section of the book, so 1.1, 1.2, 1.3, 1.4, has these key questions. And so your book will have 3 key questions per section, and it's going to be a requirement for you to understand the answers to all 3 of the key questions. So when you're taking notes, when you're reading and you're taking notes in your book, which is a skill that you really should practice and get used to before you go to college, you should at the minimum have the 3 key questions. So in case you guys aren't clear about what they are, I'll just show you, if you can see my mouse moving right here, all right, every section will have these key questions with just this purple key here. And, the key question will be, what are the steps in the scientific method? And then in bold and by another key, there'll be the key answer. Steps in the scientific method include making observations, proposing and testing hypotheses, and developing theories, et cetera, et cetera. So, when you are reading your book, at the very least, please make sure you get and nail down the 3 key questions per section. All right, so I'm not going to go through everything in chapter 1.3, but want to go over just a couple of things that I thought are important. So this is chapter 1.3 in your book, Thinking Like a Scientist. So the first key question that I want to go over are, what are the steps in the scientific method? And in fact, I think this is the only key question in this section that I'm going to go over. So the key answer that you have in your book is steps in the scientific method include making observations, proposing and testing hypotheses, and developing theories. So I want to talk a little about what these things are. So observations, it's probably like the most important thing for science. It's just kind of the most important thing. It's the basis upon which all science is founded. And so, an observation is quite simply when you use your senses to obtain information. So you see something, you smell something, you hear something. And then, of course, as scientists, when we're making observation, we are making measurements with these observations. But sometimes they're just stuff we observe. We all know the urban myth of Newton and the apple falling on his head. And, that's how he invented physics or whatever. The true story is probably that he was just watching apples fall and thinking that there was something like gravity that existed, but he was making observations in the natural world, and then he used that to, do some science. So that's what an observation is. So the important thing that I want you guys to know, and in a normal year, you would definitely be tested on this. You will probably be tested on this if I can figure out how to make you do this on some sort of test situation, but it's this figure 1.14 in your textbook, the scientific method. So as you can see here, I'll use my mouse again. Everything starts, like I said, with observations. Scientists are observing the natural world. Okay. And then from observations, they make a hypothesis. Now, in the past, you may have learn that a hypothesis is an if-then statement or an educated prediction. These things are all true, but we're going to go with a more refined definition of hypothesis, and that's that a hypothesis may be revised based on experimental data. Nope, that's not right. That's just a description. So let me define what a hypothesis is for you right now. A hypothesis is a prediction about why or what is happening behind the observation you see. So going back to Newton, he sees the apple falling, his hypothesis was that there's a force, which he ended up finding and calling gravity, a force that is causing that apple to always fall from the tree. So, hypotheses are an explanation, a scientific explanation for the observations that we see. And then, like this chart says here, a hypothesis may be revised based on experimental data. Because what happens is you have your hypothesis, you have your reason why you think things happen, and then you design an experiment to test, whether your hypothesis is supported or not, to test whether the reason why you think this is happening is actually why it's happening. When you do an experiment, it can lead to more observations that either support or disprove or don't support the hypothesis. If they don't support it, okay, you're going to go back and make a new hypothesis and then make another experiment to figure that out. But if they do support your hypothesis, then you can make one of two things. Actually, you'll just make one thing, and that is a theory. Now, a theory is just an explanation, like a concrete explanation for why the thing is happening. So your hypothesis is like your idea for why it's happening. It becomes a theory when you've tested it enough times and you're confident you can say, like, this is why this is happening. Now, people use the word theory to be like, oh, it's not like 100% and it's not like, set in stone, which is true. However, when we have scientific theories, it's very close to set in stone. And the only reason why we call them theories is because as scientists, it's our belief and our understanding that we can always learn something more, and that might make us have to change our theory. Okay, so the theory of relativity, which is something that Einstein came up with, it's called a theory not because the equations that he came up with don't work, but because we're leaving room for, if we get better technology, maybe we'll find even more complicated equations that will explain things that better. So it's important to understand that a theory is pretty well agreed upon by scientists, but we call them theories because we understand that we can make them better in the future. It's like cars, right? Like we keep building better and better cars. We don't say, oh, that car it's just a theory car, so it's not good enough. No, we take this Honda Civic and then we make a new Honda Civic, right? And that Honda Civic is just a better version of the older Honda Civic. So that's kind of how theories in science work. Now, distinguishing a theory from a scientific law is more, it's kind of like it's your summary of your theory. It's like the simple thing that you can say that explains the theory. So going back to force, you probably remember from physics, F equals ma, right? Or the laws, the Newton's laws, right? Those are just descriptions or explanations of the theory, the theory of motion, the theory of gravity. But, it's just kind of like our concise way of describing things. It's like our Cliff Notes version of the theory, since theories can be pretty complicated. So the things I want to highlight on this diagram, is really that you have to understand the real thing to understand. You are moving into more complex science. The real thing to understand is that science, there's no end point. Okay, we are always designing new experiments and refining our hypotheses, and we're always designing new experiments to refine our theories. So even the things that we're really confident in, we're always refining them and retesting them. So that's what I want you to know about the scientific method. It's always ongoing. We can always further our scientific understanding, and that's what this chart is talking about. And that's why you see a lot of circular arrows in this chart, and it's not like a linear thing where bing bam boom, we do a couple experiments and then all of a sudden we figured everything out, because science doesn't work that way. All right, science, we just keep figuring things out as things go along. All right, I'm going to pause there. If you have any questions, you should write them down, get them ready. You can email me after this lecture is over, or you can wait till we have actual Zoom class to talk about it. But, I'm just gonna give you a second to write things down, or just pause your video and go. All right, let's move on. And don't forget, like while we're doing these videos, you should definitely pause or slow things down or go back if there's something that you don't understand. And definitely, again, write down some questions that you have for me. All right, the other thing I want to talk about in chapter 1.3 is just collaboration and communication. This is just the idea that scientists work together to ensure a better outcome. No one scientist can figure everything out. No one scientist is able to do all the work that it takes to come up with these theories and to come up with these scientific laws that explain the theories or that describe the theories. Think of a potential COVID-19 vaccine. Do you want many scientists and companies to work together to make sure they have the best vaccine, to do as much testing as possible so that there aren't side effects, so like we don't grow like, extra arm or something? Of course, that's not going to happen, but to make sure that there are no side effects for this vaccine? Or would you rather everyone work alone and then release like, release vaccines that they haven't worked with other people to test, even within one company? Let's say just one pharmaceutical company, you're going to want lots of different scientists in that company working on the same vaccine so they can check each other's work and so that they can work together, get things done faster, but not only get things done faster, but also get things done accurately, more accurately, and in a better fashion. Okay, so scientists are going to collaborate and communicate a lot. And one thing I hope for this year is that we all find a way to collaborate and communicate together, even though, we're not in school together. It is 2020. There's lots of options on the internet. And so let's figure out ways to collaborate in our class. All right, let's get to the meat of the lesson. Chapter 1.4. This is where the bulk of your problems from your problem set are going to come from. All right. Problem solving is like a big thing in chemistry and in your life. The book tells you to analyze, calculate, and evaluate. All right. So analyzing means determine what you've been given in the problem and determine what you are trying to solve. Okay. You cannot figure out how to solve a problem unless you have a clear understanding about what that problem is asking. Okay. My kids come up to me all the time and they're like, Dad, I need help with something. But like sometimes they have such, little kids, right? They have such problems like describing to me what the issue that they have is. I don't know, like, and then so like I can't solve their problems or can't teach them how to solve their own problems unless they actually know what the problem is. Are they hungry? Are they tired? Whatever. Take that analogy to science. It's the same idea. If you don't know what problem you're trying to solve, like you're not going to be able to solve it. Okay. I have a student from last year who's in physics now, and he sent me a couple of problems that he needs help with. I will give you guys a suggestion. The thing that he asked me, which I love and which is the right question to ask, is where should I start, or what is this problem asking for? Because you got to figure that out before you can figure out how to answer that problem. Now, once you figure out what the problem's asking for, you need a plan for how to solve it. And so in chemistry, that usually means figuring out what equation you need. So we're going to do 2 examples right now. These examples are probably examples that some of you can solve in your head, or some of you can throw into a calculator and immediately get the answers to. However, we are using this as practice for more complicated problems that it's not going to be that easy to do that. So as we progress on in this class, the problems are going to get more complicated. And if you skip the process that I'm about to show you now, you're going to have problems later, dealing with those more difficult problems. So please, I want you guys to practice doing these problems the way that I'm showing you how to do them right now. And that's what I'm going to be looking for in your problem set so that you get the practice. Now, once you get good at it, you might come up with your own ways to write things out and to solve the problems. That's fine. But for now, we're going to try this method. It's kind of like, when you're learning a sport, you're taught to throw a certain way, you're taught to kick a certain way. But as you get better at that sport, you find better ways to throw, better ways to kick, better things that work for you. Well, that's the same thing we're going to do here. But right now I'm teaching you the basics. So please follow along. All right. So we're going to look at 2 examples. All right. So let me pull up my whiteboard here. Okay. So we are going to look at sample problem 1.1 on page 24. So pause the video and go to that page. Okay, so read the problem out loud to yourself, okay? And then what I want you to do is pause the video again, and I'm actually going to slide over to get something. So pause the video again, or think about, what is this problem asking you for? What does this problem want from you? All right, so I'm going to read this problem really quickly, or the important part. The shortest route from the Capitol to the theater is 8 blocks. How many minutes will the trip take if you can walk 1 mile in 20 minutes? Assume that 10 blocks equals 1 mile. So, what is this problem asking you for? All right, if you said this problem is asking you for how long the trip is going to take, that's what it's asking for, okay? That's what you got to know. All right, so once you know what the problem is asking for, you want to come up with your what are called knowns and your unknowns in the problem. Now, the unknowns is going to be what the problem is asking for. Your knowns is the information the problem gave you that can help you to solve the problem or help to figure out, what is like what your unknown is. All right, so let's fill this in, or actually pause right now and write down what you think your knowns are and what you think your unknowns are. All right, so here are mine. Okay, do you want to get into the habit of writing your knowns as mathematical equations? All right, so I wrote 1 mile equals 10 blocks. The distance to travel equals 8 blocks, and my walking speed equals 1 mile over 20 minutes. Or the way you read that is 1 mile per 20 minutes. All right, whenever you see a line like that, numerator and denominator, it's going to be 1 mile per 20 minutes. All right, a mile per 20 minutes. Now, I'll show you in this problem and the next problem why I want you guys to write them as fractions like that. Okay. Our unknown is how long is the trip? So time of trip is, question mark number of minutes. Okay. So you kind of got to think about it, right? Like, okay, I want to get to the time of the trip, but they only gave me the number of blocks that I have to travel, but I only know my walking speed in terms of miles. So that tells you, okay, to get to the time of the trip, I've got to get from blocks to miles. So what am I going to use? What is my known that will get me from blocks to miles? All right. I know that 1 mile equals 10 blocks. Okay. So the way that I will solve that is I'll say I'm traveling 8 blocks. Okay. And then I multiply it by, you see how, again, I made it into a fraction. I multiply it by 1 mile over 10 blocks, because when 1 mile equals 10 blocks, that means you can write that as a ratio, 1 mile over 10 blocks. So 8 blocks times 1 mile over 10 blocks. Notice that my blocks, the units, cancel, and that leaves me with 0.8 miles. All right. And it's going to be really important for you to write your units into these fractions, because getting the units to cancel out is what's going to help you get the answer. Okay. Now, once I have it in 0.8 miles, I know that I'm walking at 1 mile per 20 minutes. So I convert from miles to minutes. What I'm going to do is 0.8 miles times 20 minutes over 1 miles. Notice that my walking speed I wrote as 1 mile over 20 minutes. But in the problem, I flipped it over. Okay. Is 8 divided by 8 the same as 8 divided by 8 when you flip it over? Yes. So if 1 mile over 20 minutes, if 1 mile equals 20 minutes, you can flip that ratio over and it's not going to matter. Okay. So 0.8 miles times 20 minutes over 1 miles. Again, I'm canceling out my units. My miles cancel. 0.8 times 20 will give me 16 minutes. All right. So this will be the problem, or this will be the solution to sample problem 1.1 on page 24. I also encourage you to read through what they wrote in the book explaining how they did the problem. They did very similarly to me, but that should help you to better understand it. All right, I'm going to pause again here. As I pull up the next problem, please, write down some questions. Maybe you're not sure how I got to this. All right, rewind the video, watch it again. If after that you still have questions, write down some questions, okay? Mr. Chung, I'm not sure how you got that. Or Mr. Chung, I don't understand why this works, okay? Write down some questions that you can bring to class, okay? Because you're going to need to understand how to do this for your problem set. All right, did you write down some questions? Okay, let's move on. We are going to look at number 33 on page 26, okay? We're just going to do, or I'm going to do the problem. It walks you through it in steps, but I'm just going to do the problem. So Read the following conversion problem and then answer the questions. There are 3,600 seconds in an hour. How many seconds are there in one day? All right. So again, what are my knowns? I know that there are 3,600 seconds in 1 hour. And what is my unknown? All right. The number of seconds that are in one day. Okay. Now the question is, again, how am I going to get from seconds to days? Okay. Well, here is the next thing I want you to see. Sometimes you'll have knowns that are not included in the problem, right? So if I asked you, hey, random student, do you know how many hours are in a day? You'd be like, yeah, of course, Mr. Chung. But what you don't realize is like that's a known that the problem is assuming that you have, okay? And you do know it. You know how many hours are in a day. There are, I'll get there. All right. There are 24 hours in one day. Okay. So notice I wrote in my knowns, 24 hours equals 1 day. Okay. Because that's another known I have, even though it didn't explicitly state that in the problem. All right. So the next thing I suggest that you do is write things that are equal to each other as ratios. Now I did it in the last problem. All right. And we're going to do it again for this problem. So what I mean by that is this. If 3,600 seconds equals 1 hour, I can write it as a fraction like this. 3,600 seconds over 1 hour. Okay? 3,000 that says the same thing as 3,600 seconds equals 1 hour. But like I said in the last problem, you can also flip it over. Okay? So I can also say 1 hour over 3,600 seconds. All right? And that's going to be important later. Also, forgot to say, obviously, my handwriting is terrible. Okay, in some ways, that's why it's beneficial that we're learning online. We're just going to have to deal with it, do the best that we can. All right. The second ratio, 24 hours in 1 day, same thing. 24 hours over 1 day or 1 day over 24 hours. Okay, you can write those ratios both ways. I'm going to pause here, or you should pause your video here. Write down some questions. Maybe you're not sure how I got there. Okay, so go ahead and write that down. All right, once we know our ratios, we're going to use our ratio to determine our unknown. Okay, so I'm going to show you, it's the same idea, but I'm going to show you a new way to look at this. Okay, the problem is asking you for how many seconds are there in 1 day. So that means that my answer is going to be like X number of seconds equals 1 day. Well, that means that I can express my answer in a ratio in terms of the units, seconds per day, right? If I have the number of seconds per day, it's the same as how many seconds are in 1 day. Okay. Now, the thing that you're trying to figure out is, you know that you're going to use the seconds to hours ratio and the hours to day ratio, right? But the question is, okay, what are you going to put in to these? What are you going to put in to these ratios here, okay, to get you seconds to day? All right. So like what is going to go in there that's going to give you seconds to day? And what I want you to do, okay, is you look at your ratios that you have here. Okay? These ratios here. All right? The question is, how can we arrange them in a way where they multiply to each other and the correct units we want end up in our answer? All right? So let's take a look at seconds per hour. All right. Notice that in the answer, seconds is in the numerator. It's on top. So if that's the case, the question is, do you want to use 3,600 seconds per hour or 1 hour per 3,600 seconds? Which one is going to get us our seconds on the top? I'll give you a second to answer that in your head. That's right. We want the 3,600 seconds per hour because the seconds is on the top there. Okay. In the same way, all right, for our hours per day here, all right, which one gets our day on the bottom? 24 hours per day or 1 day per 24 hours? 24 hours per day gets us with that on the bottom. So all that being said, when we fill in these ratios, we do 3,600 seconds per hour times 24 hours per day. Notice I have an hours on the top and hours on the bottom. So again, I can cancel those out. And then my remaining units are seconds per day. And then I get 86,400 seconds per day. All right. I'm going to pause again. Okay. What questions do you guys have? Write them down. Okay. Email them to me. Bring them to class on Tuesday. I know this is tougher to do since you can't stop me in the middle of the lecture. All right. But it's important for you to come up with the questions that you have. Okay. Last thing. Like, I do not mind if you look up the answers, because for your problem set, you're going to have to show your work. So you could go into Google and type in how many seconds are there per day, right? And it'll tell you 86,400 seconds. If you can find an answer online, since you have to show me your work anyway, you know, the trick is in doing the work, right? Like that's what you actually have to learn. The answers are just a means to an end. Okay, your end is actually learning how to do the work. Okay, so, you know, in your problem set, I'm going to assign you some problems in the book where the answer's in the back of the book. They don't show you how to get there, but that gives you a guideline so that when you get to an answer, you can check whether it's right or wrong. And if it's wrong, then you can go back and ask yourself, okay, where did I go wrong? How did I fill this problem in wrong? All right, you guys are seniors now. You guys are going to college next year, and Chemistry 2 is a more challenging course. On purpose, right? I'm not here to deal with you guys like in simple mentality. Okay, you need to have a more complex. Need to have more mature mentality about your education. And what that means is you need to understand why things work. Okay, you need to understand why solving a problem this way works. Okay, the answer is what you're going to get when you understand how to solve the problem correctly. But if you understand how to solve the problem correctly, then no matter what question you're given, you're going to be able to solve it. And that's my goal for you guys this year in senior year. My goal is for you guys to have that mature thinking, okay, that leveled up problem solving that's going to help you when you go to college, so that you're going to be better prepared to deal with problems that you get if you take college science. But even if you don't take college science, this mentality of figuring out what the problem's asking you, figuring out what you know, figure out how those things relate so you can get to a solution, right? And then calculating a solution, like that's going to help you in your regular life, whether you never take a chemistry course or a science course again for the rest of your life. Okay? I'm sure you guys have a ton of questions. Like I said, write them down, send them to me, or bring them to class. Okay? And yeah, that's going to be the end of the chapter 1.3 to 1.4 lecture. Please, if you didn't understand this, you're going to have to rewatch it. Independent learning means doing things over and over again, you know, until you get it right. Like you're not born a 95% free throw shooter. You practice in the gym day after day after day after day. Repeat. Same thing with science, same thing with anything you're learning. So you watch this video again, you know, leave it on, like fall asleep to it. Watch it when you're paying attention. Watch it when you're eating dinner. If you're not, you know, if you got the time, you know, get it into your mind. That's how it's going to go with like all of these lessons, because that's what's going to help you to really get that understanding. All right. Thanks. And hope you're all doing well. Take care.